Chapter 13, The Threshold Problem Revisited. The threshold problem can now be seen more clearly because the earlier chapters have established what the threshold is actually sitting on. It is not just a psychological idea, not just an immune idea, and not just a signaling idea. It is a structural problem first. A threshold is the point at which a tissue decides that a given input is large enough, dangerous enough, or destabilizing enough to justify a shift from ordinary maintenance into inflammatory action. But that point is never fixed in abstraction. It is built into membranes, receptors, barriers, mitochondrial output, substrate pools, and the accumulated residue of prior inflammatory cycles. A healthy tissue has thresholds that are high enough to prevent constant false alarms and low enough to permit rapid defense when genuine disruption occurs. A chronically inflamed tissue loses that balance. It becomes easier to trigger, slower to reset, and less capable of distinguishing between ordinary biological friction and meaningful threat. The threshold drops, and once it drops, the body begins living in a world that feels more dangerous than it used to because its surfaces have become easier to disturb and harder to calm. This is why threshold cannot be treated as a purely signaling issue. A cell does not decide to activate based only on the concentration of a cytokine, a microbial fragment, a hormone, or a mechanical input. It decides through the material state of the membrane that receives that input. If receptor clustering is altered, if microdomains are unstable, if membrane permeability is higher, if omega-6 derived activation substrate is dominant, if oxidative fragments remain embedded in the surface, or if mitochondrial stress is already generating internal danger chemistry, then the same outside event crosses threshold more easily. A food component, a stressor, a bout of exercise, a small injury, a night of poor sleep, or a transient endotoxin pulse can all produce a larger biological response than they would have in a more stable system. The event did not necessarily become more severe. The tissue became easier to push over the line that marks the transition from normal handling into defensive escalation. The threshold problem is therefore one of the deepest ways chronic illness perpetuates itself. Every unresolved inflammatory cycle leaves behind structural evidence that lowers the threshold for the next one. Uncleared debris remains in tissue. Oxidized lipid fragments continue acting as danger-associated signals. Barriers remain slightly too open. Mitochondria remain slightly too strained. Macrophages remain slightly too incomplete in their finishing role. Membranes remain loaded with a substrate balance more prepared for initiation than completion. The next trigger then arrives in a site already leaning toward activation. That means less provocation is needed to produce more response. This is why chronic inflammatory states often feel like overreaction, but that word can be misleading. The body is not necessarily becoming irrational. It is becoming structurally preconditioned to interpret the world through lower activation thresholds. This lowered threshold state also explains why symptoms often seem disproportionate to the immediate trigger. A person eats a meal and flares. A small mechanical strain produces pain that lingers too long. Mild stress creates outsized fatigue, vascular reactivity, gut symptoms, or inflammatory discomfort. A poor night of sleep destabilizes the next day far more than expected. If these events are viewed in isolation, they look mysterious or psychosomatic. If they are viewed through the threshold model, they become more coherent. The tissue was already primed. The membrane was already unstable enough, the barrier already open enough, the mediator reservoir already biased enough, and the cleanup burden already high enough that a modest additional input was sufficient to reopen the inflammatory program. The trigger is real, but the scale of the response depends on the condition of the system receiving it. This is where the relevance of specialized pro-resolving mediators becomes even sharper. SPMs are not only important because they help end ongoing inflammation. They are important because successful resolution helps restore threshold. When neutrophil infiltration stops appropriately, when macrophages clear debris efficiently, when oxidized membrane remnants are removed, when barriers regain selective control, and when tissue stops carrying so much visible evidence of unfinished danger, the threshold for reactivation rises again. The body no longer needs to defend so quickly because the tissue no longer looks so unstable. Resolution, therefore, does more than conclude a current event. It changes the starting conditions of the next event. It helps rebuild a body that is harder to alarm unnecessarily and easier to return to baseline after normal life stressors. This is also why anti-inflammatory suppression so often fails to solve the deeper threshold problem. Suppression may reduce the intensity of visible inflammatory output, but if the structural residue of inflammation remains in place, the threshold often stays low. Debris remains uncleared. Barriers remain weak. Membranes remain oxidatively fragile. Mitochondria remain strained. The tissue becomes quieter for a time, but not more stable in its underlying architecture. Once suppression lifts or a new trigger appears, the low threshold reveals itself again. The person flares not because the old symptoms return from nowhere, but because the tissue never truly regained the structural conditions that would have made it harder to trigger in the first place. Diet becomes especially important here because threshold is partly built from long-term membrane composition. A body remodeled under omega-6 dominance, oxidative instability, poor omega-3 incorporation, glycemic volatility, and repeated inflammatory signaling will carry lower thresholds across multiple tissues. Endothelial surfaces become more reactive. Gut barriers become easier to disturb. Immune receptors become easier to activate. Nociceptive systems remain more easily sensitized. On the other side, a body with better substrate balance, better barrier integrity, preserved omega-3, derived resolution capacity, and more competent mitochondrial support can tolerate the same daily inputs without crossing into disproportionate inflammatory response. This is one reason threshold is such a useful concept. It connects the visible moment of flare to the invisible architecture built over time. The threshold problem also clarifies why healing often feels nonlinear. A person may improve overall and still have episodes that seem out of proportion. That does not necessarily mean nothing changed. It may mean the threshold has risen, but not yet enough across all tissues, all barriers, and all membrane systems to produce stable resilience under every condition. Some reservoirs remain unresolved. Some structural prerequisites remain incomplete. Some tissues have rebuilt faster than others. Threshold is therefore not a single switch. It is a distributed property of the organism. Different tissues may have different activation points, different cleanup efficiencies, and different vulnerabilities to re-triggering. Healing means those thresholds gradually rise and synchronize into a more stable whole. Seen clearly, revisiting the threshold problem after the full discussion of membrane composition, SPM biology, and failed resolution reveals that threshold is not just where inflammation starts. It is where structure, memory, and signal pressure meet. A body with low thresholds is not merely sensitive in a vague sense. It is a body carrying unresolved architecture. A body with restored thresholds is not simply calmer. It is a body whose membranes, barriers, substrate pools, cleanup systems, and mitochondrial support have been rebuilt enough that ordinary life no longer keeps crossing into emergency interpretation. The real solution to the threshold problem is therefore not simply fewer triggers. It is better completion, better cleanup, better membrane composition, and better structural control, so that the next input is received by a body that no longer mistakes every disturbance for a threat that cannot be finished. Why low omega-3 intake fails to generate SPMs. Low omega-3 intake fails to generate meaningful specialized pro-resolving mediator output for a simple reason at the most basic level. The body cannot derive a strong downstream signal from precursor material it never meaningfully stored. Resolvins, protectins, and maresins are not created from wishful physiology. They are derived from EPA and DHA that have first been absorbed, transported, incorporated into membrane phospholipids, and preserved there as part of the tissue's future signaling reserve. If intake remains low, membrane incorporation remains low. If membrane incorporation remains low, the releasable omega-3 substrate pool remains thin. And if that substrate pool remains thin, then when inflammation begins and phospholipids mobilize fatty acids from a membrane, the body has relatively little EPA and DHA available to route into pro-resolving pathways. The inflammatory sequence can still start because omega-6, derived initiation substrate, is usually plentiful. What becomes weak is the biochemical material needed to support a strong finish. This is why low omega-3 intake is not just a dietary deficiency in the abstract. It is a structural deficiency in future inflammatory control. The membrane is the reservoir from which later lipid mediators are drawn. A tissue chronically undersupplied with omega-3 does not merely have less omega-3 in circulation. It builds a phospholipid environment that is relatively poor in the precursors required for E-series resolvins, D-series resolvins, protectins, and maresins. That means the tissue enters every inflammatory event carrying less completion-capable substrate from the beginning. It still retains access to arachidonic acid-heavy icosanoid initiation chemistry, so it can recruit, amplify, sensitize, and increase permeability. But it lacks comparable depth in the later phase lipid language required to reduce continued neutrophil influx, enhance macrophage cleanup, protect tissue, and restore order. The result is not only more initiation, is weaker closure. Low intake also matters because short-term presence is not enough. EPA and DHA have to become part of the membrane architecture over time. A person who chronically underconsumes omega-3 is not just missing a nutrient in daily intake terms. They are failing to build and maintain the membrane reservoir from which SPM production later depends. This is one reason the effects of omega-3 status are often delayed and cumulative. The body does not generate a strong pro-resolving system from occasional exposure. It generates it from repeated incorporation and phospholipid remodeling. When intake stays low for long enough, tissues are remodeled in the opposite direction. The membrane remains more heavily defined by other fatty acid classes, especially omega-6 derived substrate, and the future mediator landscape becomes biased toward escalation rather than resolution. There is another level to this as well, which is substrate competition. In a body with low omega-3 intake, the problem is not only that EPA and DHA are scarce. It is that the shared membrane and enzymatic spaces are filled by something else. Arachidonic acid-related substrate continues occupying phospholipid positions and continues dominating downstream COX and locks traffic during inflammatory activation. That means low omega-3 intake weakens SPM generation in two directions at once. It reduces the availability of a necessary precursor, and it allows competing substrate to remain relatively dominant in the same structural and enzymatic territory. The body therefore becomes increasingly practiced at generating the front half of inflammation and increasingly underbuilt in the back half. This is especially important because SPM generation is not a luxury pathway. It is part of how the body prevents early-phase inflammatory force from becoming chronic tissue damage. Low omega-3 intake leaves the body with less material for mediator class switching, less support for downstream conversion into pro-resolving families, and less capacity to push macrophages toward efficient erythrocytosis and tissue cleanup. In practical terms, the body can still call for help, but it has less biochemical authority to tell the site when enough help has arrived. It can still inflame, but it resolves with less force and less precision. Seen clearly, low omega-3 intake fails to generate SPMs because SPM biology is built on stored precursor abundance inside membranes, not on vague nutritional virtue. If EPA and DHA are not meaningfully supplied, they are not meaningfully incorporated. If they are not meaningfully incorporated, they are not meaningfully releasable during inflammation. If they are not meaningfully releasable, downstream conversion into resolvins, protectins, and marazins remains weak. The body then enters inflammation with a full ignition system and an underbuilt braking system. That is the deeper consequence of low omega-3 intake. It does not just reduce one beneficial nutrient. It lowers the body's structural ability to complete inflammation as a successful program. Membrane saturation thresholds. Membrane saturation thresholds refer to the point at which the fatty acid composition of a membrane stops being a neutral background detail and begins determining whether that membrane behaves as a stable control surface or as a structurally fragile, overly reactive, or poorly adaptable one. The term saturation here is not just about how much saturated fat is present. It is about the overall degree of fatty acid saturation versus unsaturation built into phospholipid architecture, and therefore about how tightly the membrane packs, how easily it oxidizes, how mobile its proteins remain, how permeable it becomes under stress, and how its stored lipid reservoir will behave once inflammatory activation begins. A membrane does not need to be all one thing to cross a threshold. It only needs to become compositionally weighted enough in one direction that its behavior starts changing in a decisive way. This matters because membranes are not infinitely tolerant of compositional drift. A membrane enriched too heavily in highly unsaturated fatty acids may gain signaling flexibility and dynamic fluidity, but beyond a certain point it also becomes easier to peroxidize, easier to disturb, and easier to convert into a chemically noisy surface under oxidative or inflammatory stress. A membrane enriched too heavily in saturated structure may gain durability and resistance to oxidative injury, but beyond a certain point it may also lose some of the fluid behavior needed for receptor clustering, vesicle fusion, signal propagation, and adaptive membrane remodeling in certain tissues. The body therefore operates within functional thresholds. It is not aiming for maximal saturation or maximal unsaturation. It is aiming for enough structural firmness to preserve order and enough fluid responsiveness to preserve function. When the membrane crosses too far in either direction, tissue behavior begins to change. The relevance to resolution biology is direct. A membrane that sits below the threshold of usable stability becomes too vulnerable to the very inflammatory sequence it is supposed to survive. Oxidative stress damages its polyunsaturated components too easily. Receptors begin reading inputs through a noisier surface. Phospholipase release draws from a reservoir that may be rich in signaling potential but chemically fragile. Under those conditions, the membrane may carry omega-3 derived substrate in theory, while still failing to preserve that substrate well enough for strong downstream SPM generation in practice. Resolution potential drops because the membrane crosses a threshold where unsaturation is no longer serving mainly as strategic signaling material. It is becoming a liability under load. At the same time, membrane saturation thresholds are tissue-specific. Neural tissue immune cells, endothelial surfaces, epithelial barriers, and mitochondrial membranes are not solving the same structural problem. The brain and retina require membrane behavior that would not be optimal if every phospholipid surface were built for maximal rigidity. Immune cells need enough membrane adaptability to reorganize receptors, form synapses, engulf debris, and transition between activation states. Mitochondria need inner membranes capable of preserving gradients while still maintaining specialized curvature and protein organization. That means the threshold is not one global number. It is a functional boundary defined by what that tissue must do and how much chemical stress it is under while doing it. This is why membrane saturation thresholds should be understood less as a dietary slogan and more as a systems principle. The real question is not whether a membrane is saturated or unsaturated in a simplistic sense. The real question is whether the membrane has crossed into a region where its structure now undermines its own signaling and recovery capacity. If it becomes too unsaturated relative to oxidative protection, the tissue becomes easier to inflame and harder to resolve. If it becomes too rigid relative to its signaling demands, the tissue may preserve order at the cost of responsiveness and adaptive function. Health lies in maintaining a composition that keeps the membrane below the threshold of fragility and below the threshold of maladaptive rigidity at the same time. Seen through the lens of this book, membrane saturation thresholds help explain why lipid biology cannot be reduced to a battle between saturated fat and polyunsaturated fat. The body requires both stability and dynamic signaling substrate. It requires membranes firm enough to survive inflammatory stress and flexible enough to carry out the receptor, transport, and mediator functions that living tissues depend on. The critical issue is where the membrane sits relative to its functional threshold. When it remains inside a stable range, resolution potential is preserved because omega-3 derived substrate can be stored, protected, and later converted into meaningful pro-resolving output. When it drifts too far toward instability, that same substrate becomes too easy to damage. The body then loses not only structural coherence, but part of its ability to end inflammation from the membrane level upward. Nonlinear conversion to SPMs. Conversion to specialized pro-resolving mediators is nonlinear because the body does not turn EPA and DHA into resolvins, protectins and marazins in a smooth, proportional, always-on way. More precursor does not automatically produce more SPMs in a simple straight line. The pathway behaves more like a conditional system with thresholds, bottlenecks, timing gates, and phase-dependent shifts. EPA and DHA have to be present in the right membrane pools, released at the right time, routed through the right enzymes, and processed inside a tissue environment that has actually transitioned far enough beyond early inflammatory escalation to allow pro-resolving chemistry to matter. If any of those conditions are missing, more omega-3 can still increase structural potential without producing a proportionate increase in downstream SPM output. This is why people often misunderstand omega-3 biology. They assume substrate behaves like a dosage-response drug. In reality, the body treats SPM generation more like a context-sensitive phase change. The first reason the conversion is nonlinear is substrate threshold. Very low EPA and DHA incorporation produces very little meaningful SPM generating capacity because the membrane reservoir is simply too thin. But once membrane levels rise to a more functional range, the tissue may suddenly gain much greater access to downstream mediator generation because enough precursor is now available in the releasable phospholipid pool to influence class switching and later phase signaling. That means the early part of the curve can be flat, then a more meaningful shift appears once a certain degree of incorporation has been achieved. In other words, small increases at low tissue levels may not produce obvious resolution effects, while the same increase at a higher baseline may matter much more because the membrane has crossed from token presence into functional availability. The second reason is enzymatic competition. EPA and DHA are not converted in isolation. They compete with omega-6 derived substrate, especially arachidonic acid, inside shared COX and LOX pathways. If a tissue remains heavily dominated by arachidonic acid-heavy membrane composition and early-phase inflammatory signaling, then additional EPA and DHA may produce relatively modest downstream change at first because the enzymatic traffic is still crowded by initiation chemistry. Then, once membrane composition shifts enough or inflammatory tone changes enough, the same amount of added precursor may begin to exert a much larger effect because the competition landscape has changed. This is another form of nonlinearity. The system can remain resistant for a while, then become more responsive once substrate balance crosses a meaningful threshold. Timing makes the curve even less linear. SPMs are not generated as though the body were constantly trying to maximize resolution chemistry under all conditions. They belong to a later phase of the inflammatory sequence. Early in inflammation, the tissue is usually prioritizing initiation and amplification. Only later, if the event is progressing properly, does mediator class switching begin favoring pro-resolving output. That means a person can have reasonable EPA and DHA incorporation and still produce little SPM activity in a given moment if the tissue has not yet entered the phase where resolution pathways are supposed to dominate. The same substrate, therefore, has different consequences depending on when in the inflammatory sequence it is being mobilized. Time is built into the conversion curve. Oxidative stability adds another layer of nonlinearity. EPA and DHA are highly unsaturated and therefore vulnerable to peroxidation. In a relatively stable tissue environment, increased incorporation can raise the reservoir for SPM production. In a highly oxidized environment, however, part of that added substrate may be damaged before it can be cleanly converted into useful pro-resolving mediators. That means the relationship between stored omega-3 and actual SPM output may flatten, stall, or even become inefficient when oxidative stress is too high. The tissue may contain more precursor on paper without gaining proportionate resolution capacity in practice. The system is being pushed from one side by substrate availability and from the other by substrate fragility. Cell type and tissue phenotype also matter. A macrophage in an effective resolving phenotype does not handle DHA and EPA the same way as a tissue still dominated by neutrophil-heavy recruitment, endothelial activation, and early cytokine escalation. The same precursor pool can therefore produce different downstream mediator behavior depending on which cells are active, what phase the tissue is in, and whether the site is organized around cleanup or continued defense. This is one reason conversion looks inconsistent from the outside. It is not inconsistent at the biological level. Is conditional. The precursor is entering different local systems with different probabilities of routing into SPM production. This helps explain why the benefits of omega-3 often appear delayed, threshold-like, or context-dependent rather than steadily proportional. Structural incorporation may rise before mediator output changes dramatically. Mediator output may rise before tissue-level clinical improvement becomes obvious. In another case, membrane incorporation may improve while SPM production remains weak because the person is still living inside repeated gut-triggered immune activation, oxidative overload, poor mitochondrial support, or omega-6 dominant competition. Then, once one of those constraints improves, the same precursor pool begins producing a larger biological effect. That is classic nonlinear behavior. The system is not responding to one variable in isolation, is responding to a network of gates. Seen clearly, nonlinear conversion to SPMs means the body does not resolve inflammation according to a simple input-output equation. It resolves when membrane substrate, enzymatic access, oxidative protection, inflammatory timing, immune phenotype, and tissue stability align strongly enough that EPA and DHA-derived mediators can actually take command of the later phase. More precursor helps, but only within that larger architecture. The real lesson is that omega 3 should not be judged by a straight-line expectation. Its deepest effects emerge when enough structural and biochemical conditions are met that the system can cross from merely carrying resolution substrate to actually converting that substrate into the chemistry of completion. The concept of resolution activation. Resolution activation is the point at which the body stops treating inflammation as a problem of force generation and starts treating it as a problem of completion. That shift sounds subtle, but it marks a real biological transition. In early inflammation, the system is organized around access, recruitment, amplification, and acute defense. Blood vessels open. Neutrophils arrivent. Eicosanoid cascades intensify. Pain thresholds drop. Oxidative chemistry rises. The tissue is prioritizing control of the threat. Resolution activation begins when the tissue receives and successfully acts on a different class of instruction, one that says further escalation is no longer the smartest use of energy or structure. At that point, the biology of the site changes. Recruitment begins to taper. Macrophage cleanup gains priority. Barrier restoration becomes possible. The inflammatory event stops being an expanding reaction and starts becoming a controlled dismantling of the reaction itself. This is important because resolution is often described as though it begins automatically once the trigger fades. That is too passive. Resolution activation implies that the body must actually cross into a later phase. It has to turn on the mechanisms of closure with enough strength that they can overtake the inertia of the earlier inflammatory program. In practical terms, that means enough EPA and DHA must already be stored in membrane phospholipids, enough of that substrate must be released and converted downstream into specialized pro-resolving mediators, and the cellular environment must be ready to respond to those mediators. Neutrophil-heavy logic has to stop dominating. Macrophages must become better finishers. Endothelial and epithelial surfaces must begin closing rather than continuing to open. The tissue has to receive a credible biochemical message that the emergency phase is no longer primary. Resolution activation is that moment of phase command. This concept helps explain why so many inflammatory conditions persist even when the body is no longer facing a major acute insult. The issue is often not that inflammation cannot decline at all. The issue is that the body never fully activates the later program strongly enough to take control. It remains in a low-grade state of initiation and amplification, repeatedly restarting the first half of inflammation because the second half never becomes dominant. Debris remains. Barriers remain weak. Oxidized membrane fragments remain visible. Pain remains justified. The tissue may show partial improvement, but it does not cross the threshold into organized closure. Resolution activation, therefore, means more than having some SPMs present. It means having enough pro-resolving pressure, enough structural stability, and enough metabolic support that the tissue actually switches from escalation mode into completion mode. This also makes clear why resolution activation is a threshold phenomenon rather than a gentle linear fade. A tissue may carry some omega-3 derived substrate and still remain stuck because the inflammatory environment is too dominated by arachidonic acid-heavy signaling, oxidative damage, enzymatic crowding, or repeated retriggering. Then, once membrane composition improves enough, cleanup burden drops enough, barrier function improves enough, or mitochondrial support rises enough, the same tissue can begin behaving differently in a way that looks disproportionate to the size of the change. That is because the system has crossed from insufficient late-phase influence into sufficient late-phase influence. Resolution is no longer just possible in theory. It is activated in practice. Seen clearly, the concept of resolution activation gives the back half of inflammation the same seriousness usually given to the front half. Initiation has triggers. Amplification has cascades. Resolution also has an activation point. It is not a passive settling. It is the moment when the body begins issuing a different command. Stop recruiting, start clearing, stop expanding, start restoring, stop defending as though the danger is still growing, and start rebuilding as though the danger can now be finished. That is what makes resolution a real biological phase rather than just the absence of one.